I mentioned, I don't know, it's been a while now, that our unit is on solutions. Really, we're focusing on liquids, dissolving things inside water. If I were to take salt and put it in water, the salt doesn't just disappear. It's not a magic trick. The salt in water is actually doing something else. We say it dissociates. You guys recall that term? Dissociate means that it breaks up into ions. Side note, by the way, I like little side notes. Magicians. I would say, especially like magicians of years and years ago, the magic, I'm using my fingers here, they would do isn't really magic, right? Often they would use, like, say, chemistry tricks in order to do magic. Does that make sense? You make something disappear, but really what actually happened was a chemical reaction instead. Does that make sense? So, let's do another bit of review here. Let's say that we took KCl and we added it to water. It's just breaking up into pieces. Does that make sense? The KCl is not gone, it's been ripped apart. I love that analogy. I hope it is vivid enough that you remember it. There's a whole bunch of you guys here that are fairly strong. But if we had 1 million first graders come into this classroom, they would keep you apart. Does that make sense? Like, you are not strong enough to beat 1 million first graders. Well, that's what happens when you've got solid stuff. Where's that picture? It's way back here. Yeah, this one will do. When you've got something solid, these anions and cations, they have a lot of strength to them. Ionic bonds are fairly strong. But water, if there are enough water molecules, can literally rip this thing apart and surround them. And that's why the solid disappears or dissociates. Okay, let me move on. You guys look like you know what I'm talking about here. Okay, let's say you want to then make a solution in my lab. There's 2 main ways of making a solution, and I like the analogy of making juice. So I'm going to make juice today. One of the ways you can make juice is by using like the solid crystals. You add little solid crystals to water. Does that make sense? But there's a second way as well. You can take like the concentrate stuff and you add that to water. Both of which work, but they require slightly different methods of making solutions. So let me start with making a solution of something solid. And so I'll demo it here. Let's say I want to make a solution of orange juice. Last day, when you guys watched that video, I talked about wanting to put a number on solutions and rank them quantitatively. Do you guys recall that? So if I asked you to make like a 5.7 moles per liter solution, we would need to weigh out a certain amount of stuff. So first thing you would do then is you're going to want to grab your solid crystals and you're going to want one of these little weighing dishes. And you're hopefully going to know how much you need it to weigh to give. So I mean, imagine you're on the scale here. Grab my scoopula. Where did I leave it? Here it is. Grab your scoopula and add your crystals. You guys can come closer if you want, by the way. You don't have to stay where you're at. And add your crystals to the dish. Now you can't see it. Okay. So at some point you're probably going to weigh out your crystals. Now, with these being orange juice crystals, I'm not overly worried about their safety. But I mean, we will work with other stuff that is poisonous and toxic and unhealthy. So as a general rule of thumb, if you are like putting stuff on the dish right here, it is okay to like kind of put some back here, but please make sure you don't spill it everywhere. Does that make sense? Because that's not going to be quite as good. So I would say pour into the dish, and then if you need to, put it back into the container if you have too much. Usually it's better though to like try to undershoot how much you need and try to just add it little bit by little bit, because you can always add a little bit more. Sometimes it's very difficult though if you have too much to put it back. So far so good. Okay, now our goal is to try to add this to a certain container, and this is the container we want to add it to. The reason why is that we need to very precisely and accurately measure water out to this line. However, here's the problem with adding stuff to a volumetric flask. If I pour these crystals into here, let's say I use a funnel, I need to stir it up. And this thing does not go in very well. If I use this side, it might go in a little bit, but does that make sense? So whenever you want to make a solution then, once you've weighed out your solid crystals, grab another like small beaker and add the crystals to that beaker. And what you're going to do is you're going to add water to it in the beaker so that you can actually stir inside the beaker. Does that make sense? Sometimes in our lab, we'll use tap water. One of the problems with tap water, though, is tap water is not pure. There are dissolved ions inside of it. So occasionally, we'll use distilled water, which is like, I'll just buy it in a jug like this. And this should be 100% pure water. There's no other dissolved ions inside this. So, stir up your solution. Pour it into here. Here's the problem. You guys see how there's just a little bit of sugary crystals left at the bottom of there? Yeah. Well, I just went through the whole process of weighing them on this thing right here, but now I'm leaving some of them in there. That's going to make me less accurate or precise. Less accurate. Because accuracy is whether you're correct or not. So I can't leave extra crystals in there. So usually what you want to do is you want to wash the beaker out a second time, just to add a little bit more water. And hopefully what can happen is you can kind of rinse the rest of them out of there and into here. And maybe I can see like a few left in there. Maybe I'll try it one more time. Make sense so far? Here's the problem. This particular measuring device only measures one volume. It measures 100 milliliters. It has to get filled exactly to that line. One of the issues with working with this is that, let's say you fill the water up to here. You can't just pour some of the water back out. Why? Yeah, some of the juice crystals will go out with it. And again, we just took all of that time to measure the exact amount of juice crystals. So if I pour some back out, it will no longer be accurate. Does that make sense? So you have to be very, very, very careful when you're adding the rest of the water to here. So I mean, if you feel comfortable, you can maybe try to pour it directly in. But I would say most kids, myself included, use an eyedropper to finish this off. So I might pour it until.
At your building, Mr. Schultz.
Showing them how to make juice.
How to make juice?
It's our first lab, so it's simple.
All right then.
So I just use the eyedropper. Do you guys know much about how water works when it comes to a meniscus? Have you guys ever heard that term before? Before I get there, I don't know if you guys can see this, but there's like a little, like it almost looks like a contact lens on the bottom where it has like that concave shape to it. You guys know that? When you're measuring, what ends up happening is water gets drawn up the sides of the glass, and that the top is actually not where the water happens to be. It's a bit of an optical illusion. So when you want to measure, you want the very, very bottom of that little contact, the meniscus is what we call it. You want that to be at the line you're looking for. Otherwise, you're not accurate. So right here, it looks like the top of my meniscus is at that line, but I want the bottom of the meniscus at that line, so add a little bit more. Ideally, again, drop by drop. Hopefully you guys can see that the bottom of the little curvature is right on that line. Does that make sense? Now I have accurately used this tool. What's precision then on this tool? Well, precision is based on how many decimal places this tool gives. And this gives 100 milliliters plus or minus 0.20. So like that means this thing goes to the nearest 100. Like it's 100.00. So actually it gives quite a few different decimals. Like it gives 5 sig digs. Does that make sense? Sometimes maybe the best way of talking about precision is how many sig digs do you get? If you get more sig digs, it's a more precise tool. So precision is based on what the tool tells me it's using. Accuracy is that I use the tool properly. If I dumped a whole bunch more water in here, the measuring tool is still precise. I just screwed up. Okay, last step. We still actually want to stir this a little bit. So that's where this or this comes into play. This is a cap. So sometimes what we do to mix is, since I can't put this thing inside here, we tip it upside down. This is called inverting to mix. And this should hopefully help mix it up a little bit. One of the problems with that, I just got a little bit on my finger. So it's orange juice. I'm not worried about washing my hands. But if this was something poisonous or corrosive or something like that, that'd be bad. So often what we do as well is we add this, it's like saran wrap. You guys know, like you use to wrap your food after you eat it. Only it's a lot thicker, like it's very stretchy still. But sometimes we wrap this over top as well. And that'll just help with an extra little bit of a barrier so that way stuff doesn't move. So there. We've now made a solution, and hopefully we know its concentration, because we measured a mass and we measured a volume, and that can help us find a concentration. Does that make sense? You guys can just sit back down, I guess. So that's the process you guys are going to go through when you do the lab on Wednesday, I guess, is our first lab. So there are two measuring tools I used in that process. One of the measuring tools is called an electronic balance, but usually we call it a scale. The scale we used to measure the solute. The solute was in grams. That's a mass. The other tool we used was called the volumetric flask, and it measured volume. I guess that makes sense. And that was probably in milliliters. If we know the mass and we know the volume, we can then find its concentration in one of three ways. And these are the ways you did in that video. One of the ways is called moles per liter. Another one of the ways is called parts per million. And then the third one was weight over volume. Do you guys remember those? Okay, we'll do some more examples later, but if we have those two numbers, we have to measure them in a lab. If we do that, then we can find a concentration. By the way, if we find a solution and we know its concentration, we have a name for it. We call it a standard solution. So if we know its concentration because we made it, we were very accurate with our measurements. Accurate meaning correct. That's the name for it. So here's kind of a picture of what I kind of just showed you, only this one's not really correct. Don't add the solid stuff directly into the volumetric flask, because chances are you won't be able to stir it. So maybe like a little side note here, put it into like dissolve in a beaker instead. And then add water until it gets to the line. But don't add the solid stuff directly into here, because you can't stir. Does that make sense? Okay, there is a second way of making solutions. It's by using dilution process. I'm not actually going to make frozen concentrated orange juice because I'm sure you've all seen it before. But basically the idea there is you take a very, I don't want to use the word strong, because what does strong mean in chemistry? Yeah, strong means it's a good conductor. But I mean, you guys ever try to eat like the frozen concentrate stuff before? It is, like, I can get through a couple of spoonfuls, like it is thick. Like it's not meant to be eaten straight with a spoon. Right? So strong is the word you might use in real life, but it's really concentrate. So you take the concentrate stuff, and we have a name for that. Anything that is very concentrated is called a stock solution. And you add water to it. Basically, you're trying to make it weaker. Only weaker is not the chemistry word. I want to use the word dilute. Diluter. No, that's not right. You want to make it more dilute. Okay. If you add more water to it, it's not quite so strong. For this particular thing here, we have a formula. And the way this formula works is it's a before and after formula. If you know the volume of your stock solution, and you know the concentration of your stock solution beforehand, it is going to be equal to the volume of your standard solution and the concentration of your standard solution. This, on this side right here, the numbers you're going to use here, these are going to be numbers for the concentrate stuff. Whereas these numbers right here are going to be numbers for the, like, after you're done, when it's diluted. Let me do an example. I think that's what's up next here. Oh, picture slide. How do you make a solution by diluting it? You just add water. Like, there's nothing special to it. Like, just add some water. So let's try an example here. Let's say that I give you some concentrated HCl, and it's 36%. Very concentrated. Concentrated enough that if you spill a drop of it, I did this once before. Like, I spilled a drop on my jeans. Like, the hole after it was done was like that big. Well, that's just from like 1 or 2 drops. Like, it's concentrate acid. Let's say that you don't want to use that much concentrate stuff, but you'd rather have 4 liters of the 10% concentration. How much of the concentrate stuff should you use? So here's how this formula would work. It's V1C1 equals V2C2. We actually have 3 numbers to plug into this formula. These numbers right here are for the concentrated stuff, and these numbers right here are for the diluted standard stuff afterwards. So I know volume too. When I'm done, I want to have 4 liters. I also know how concentrated I want the after stuff to be. I want it to be 10% concentrated. However, I don't know how much of the really concentrate solution I should use. I don't know my initial volume. I'm actually looking for that. But I do know how concentrate the initial stuff was. It's 36%. Does that make sense? So I teach you guys all math. If this is a variable like x, how do you get x by itself? Yeah, divide by 36. So divide this side by 36. Divide this side by 36. There. Now I've found my initial volume. How much concentrate HCl should we measure? Take a look at your units here. Here you've got liters. You see how you have a percent sign on both of these guys right here? What will happen to the percent signs if one's on the top and one's on the bottom? Yeah, absolutely, yeah. They cancel. They cancel. So someone who's got a calculator, help me out here. What is 4.00 times 10 divided by 36? 1.1 repeating? Should be sufficient for now. What units is that? How do I know? It's the unit that's left. It's the one that didn't cancel. Okay, here's a good time to talk about accuracy and precision. If you were in a lab and you needed to measure some of these values, 4.00, hopefully that's accurate. I don't actually know whether it's accurate or not. But hopefully the person who used like a big container, if it was supposed to be filled to this line, hopefully they actually filled it to that line. Does that make sense? That's accuracy. But I can talk about its precision. This thing is quite precise. It has 1, 2, 3 sig digs. That's its precision. Does that make sense? If someone measured at 4.000 liters, that's even more precise. Does that make sense? That being said, this only has 2 sig digs, and this only has 2 sig digs. So this last number right here is based on your precision. When you guys talk about sig digs, you probably never use the term precision, but that's what it's based on. Whatever is the least precise measuring tool you use, that's what you have to base your final calculations on. Let's say that I were to use like the best scale I had in the world. The scale went to 9 decimal places. And then I needed to measure something in terms of a volume. And in terms of measuring that volume, I used this tool right here. How precise is this tool going to be when I'm trying to use it? Well, like, it's either 900 or 1,000 or 950. How helpful is that? Is this the best measuring tool I could use in terms of like precision? And so, well, no. But if I were to use this measuring tool, you see how there's all those different lines on the side there? This is more precise now. Does that make sense? So based on that, sig digs are based on the least amount of precision. So this is going to be 1.1 liters. 2 sig digs. Does that make sense so far? Cool. Let's just do some more examples then, because that's most of what I think I have left in this set of notes. Right? Is it mostly just examples? Okay. This method here is back to making something with a scale. The reason I know that we're making this example with a scale is because, look, there's a grams right there. So imagine that rather than us using juice crystals, let's say I gave you some calcium phosphate and we dissolved it in a 100 ml volumetric flask. Let's find the concentration. So one of the things I would have shown you guys last day, or on that video, is if you can take, say, grams and multiply by, like, say, a mole per gram. See how that would cancel? That would give you moles. And then one of the best ways of finding a concentration is in moles per liter. So I already know how many liters we're going to use. We're going to use that many liters. Where did that number just magically show up from? Do you guys know how to convert milliliters to liters? Yeah, I just divided by 1,000. So that's where this number here came from. I'm already halfway there. A concentration is how many moles you have in a liter. That's typically how we measure it. It's one of the ways. Well, I just need to then figure out how many moles there were. Well, I actually have the start of that. Here's 14.5 grams. But the problem is I need to try to find a way to convert grams into moles. Where do I find a moles grams type of number from? You guys recall how to do that? What did you say? Fantastic, we need the molar mass, yeah. So to find the molar mass, we need to first know what calcium phosphate even is. What is calcium phosphate? That's calcium. Do the charges fit? Calcium's charge? Phosphate's charge? So one's a 2, one's a 3. So there's calcium phosphate. Okay, calcium. I think it's 4008. What did you say it was? Oh, that's sodium, not calcium. That's why. We'll need 3 of those. I don't think I know phosphorus. Is it 3097 or something like that? Oh, there it is. Yeah, 3097. That was right. How many phosphoruses do we need? Phosphori. Do we need? Yeah, 2. Because there's this 2 right here. Anybody know oxygen's molar mass? Right on the dot. Do those zeros matter? For precision and sig digs, yes they do. Because it's more precise, because you have more digits. How many oxygens do we need total? Yep, 8. Alright, so grab a calculator and find a molar mass. Need a calculator here. .08 times 3 plus 3097 times 2 plus 16 times 8. 31018. Okay, that is how many grams there are in 1 mole. Or if you like my analogy of donuts, if you were to go buy a dozen donuts, it would have weighed 310 grams of this type of donut. Where does that number go here? Does it go on the top with the mole or on the bottom with the gram? It goes on the bottom with the gram. Yeah. Let me just show you 2 different ways of writing it. You could have written 14.5 grams multiplied by 310.18 grams per mole. But hopefully you guys can see how this gram right here and this gram right here, that doesn't cancel. Does that make sense? So multiplying is not useful. But if I divide by 310.18 moles per gram, the grams will cancel. So if I did that 14.5 divided by 310.18, I ended up with a 0.0 0.0467, etc. You guys get that value? 14.5 divided by the molar mass gives you this number. Did you guys get that? I'm not done though, because concentration gets measured in moles per liter. So now that I know how many moles I have, I'm going to divide by how many liters there was. So take that answer in your calculator and divide by 0.1. Well, actually, divide by 0.100. Here's your final answer, 0.467, capital M. Did you guys remember from my video what capital M stands for? Yeah, it's just a shorter way of writing moles per liter. You could have written this as a 0.467 MOL over L, but like a faster way of doing it is just capital M. Is this a concentrated solution? No, it's not super concentrated. Do you guys remember what like the higher most limit of solutions concentrations tends to be? Yeah, I'd say the strongest thing I have in my lab, I probably have some sulfuric acid that's maybe 18, and I have some hydrochloric acid that's about 50. And that is like super corrosive stuff. Like it is very concentrated. Okay. Generally, anything greater than 1 mole per liter is pretty concentrated. So, I mean, it's not that concentrated, but now we actually have a ranking, a numerical value that we can attach to a solution that says this is a concentrate solution and this one's not. Kind of like with the picture I had way back here. Where that was. This is a very concentrated glass of juice. This might be 14 moles per liter. This one might be 6 moles per liter. This one might be 1 mole per liter. This guy might be 0.3 moles per liter. Does that make sense? We can actually put a ranking on these things now and say how concentrated they are. Any questions? Okay. Why don't we take a break before we finish the last examples? Because it's been a while. Why don't you guys take 5, and when you come back, we'll do 3, 4, 5, 6. All right, so we got 4 examples left. Take a break, though. How am I doing so far? You guys still with me, or did I lose you?
We're good.
So far, so good?
I just don't get why concentrate.
Okay. Maybe a few more examples can sometimes help with that. So ask me again after the next 4 examples. So okay. Okay, let's try another example here. Let's say that I give you this information. You're going to add some water to a cleaning solution. We're diluting this. So we have some fairly concentrate stuff. Apparently. So you have a fairly concentrated solution. 2.4 moles per liter is actually fairly concentrated. It's well over 1. And you're going to add some water to it. This is one of the very few times in chemistry where I actually have a formula to give you. The only time we have a formula so far is if you're diluting something. And that's the V1C1 equals V2C2. The biggest struggle with this then is, where do numbers go? So this is like the before you dilute, and this is the after you're done diluting stuff. So do we know what we had before we added water? Yeah, we had 0.200 liters, and it was 240 moles per liter. After we're done, actually we know a number here. After we added water, how much water was there total? 1 liter. Here's the problem though. We don't know what that second concentration was, so I'm just going to leave C2 sitting there as a variable. How do you solve for C2? Yeah, I guess you're dividing by 1. You should probably show the work. So divide by 1 liter. Divide this side by 1 liter. This to 0. There. Granted, dividing by 1 mathematically is not that useful. But the reason why I want to show it here is for units. What units will cancel? Yeah, this liter right here will cancel that liter right there. So what's the only unit left? moles per liter, which is probably the most common way that we measure concentration. There are other ways though, so hopefully you guys recall parts per million and weight over volume, because those can happen too. But moles per liter is a way we measure concentration. So I just need 0.2 times 2.4. I got 0.48. Anybody else get that? Is that the right answer? Why would he ask unless he had a point? That's not the right answer. Anybody know why? It has to do with precision. This was measured with the precision that gave us 3 sigdigs. This was measured with precision that gave us 3 sigdigs. This was measured with precision that gave us 4 sigdigs. But we have an answer that has precision of only 2 sigdigs. So I know it seems kind of silly to add a 0, but the point behind it is we need 1 extra digit of precision. That's why sigdig rules were developed. Because all of these were measured with a fairly reasonable degree of precision. This one needs that same amount. At least 3. Does that make sense?
So we only get 2 sigdigs and we need 3, just adding 0?
Yes. Like if the calculator literally stops the next digit, I mean the next digit is a 0 then. Does that make sense?
Yeah.
Alright, another example. Are we doing dilution or are we making something using a solid? Well, based on the information that I'm given here, it looks like we're measuring how many grams of solute. So, of the 2 methods of making juice I showed you, one is using solid crystals, one is using the concentrate frozen stuff. This is the solid crystals. I don't have a formula to give you here. So, in terms of this one here, like the C1V1 equals C2V2, doesn't even work. Because, I mean, sure, maybe you have a concentration and you have a volume, but it's not enough to fit the formula. So, this formula will not work. We have to try to solve this by making our units fit together. So the first thing I'd say then is, well, what units do we have? We have 0.200 capital M. What does capital M really mean? Moles per liter. Well, this guy right here is milliliters, but I can convert it to liters fairly easily. How do you make a milliliter a liter? Okay, so I'm just going to throw off to the side here. 50.0 milliliters is actually 0.0500 liters. I'm just going to multiply these. Now, granted, I know what to do because I've done this for a long time. But I'm hoping that you'll see why I chose to multiply these based on units. What is going to happen with our units once we're done here? The liters will cancel. That's useful. Now, don't actually hit that in yet, though. Pause. What are we looking for? Grams. What would the units be if I actually multiply these 2 numbers? Don't want moles, I want grams. So in one complete step, I'm going to add 1 more ratio here. I don't want moles. So if I found a gram per mole ratio, do you guys see how this one's on the top of a fraction? I know it's way back here. And this one's on the bottom of a fraction way over here, but one is on top, one's on the bottom. What I really need is a grams to mole number. How do I find such a number? Yeah, molar mass on the periodic table. So, first, what's sodium hydroxide? NaOH. Does that fit together perfectly like that, or do I need to put any 2s somewhere? It fits. It's a 1 and a 1 for charges. So. Sodium is 2299. Oxygen is 16. Hydrogen is 101. So this ends up being 40 right on the dot. Where does the number 40 go? Does it go up top here with the grams or on the bottom of the moles? It goes up. It goes up top here with the grams. Yeah, it's 40 grams. That's what a dozen donuts weighs. Only we don't measure in dozens, we measure in moles. So hopefully you can see how I put all 3 numbers together. This moles will cancel way over here with this moles. This liter will cancel right next to it with this liter. What's the only thing left? Grams. Isn't that what we wanted? How many grams of solute we get? So now, use your calculator. I would recommend. Don't do it in steps. Try to do it all at once. So take 0.2, 0, 0, times by 0.0500, and times by 40.00. My calculator told me that this was the answer. Is that the right answer? No. If I was measuring this on a scale, this scale would only measure to the nearest tenth. That's not actually that good of a scale. I have scales that measure way more decimal places based on precision. Today's a good day for precision. So this deserves 3 decimal places, this deserves 3 decimal places. Or 3 sig digs is sort of what I mean. 3 sig digs, 3 sig digs. We need to get out a fairly precise scale to measure it to 0.400 grams. That's how much, like, you know how when I weighed out my orange juice crystals? That's how much orange juice crystals I should pour onto my little scale, little measuring cup on there. That makes sense? My best recommendation is the sooner you can figure out how to use units to cancel them, the easier your life will be in chemistry and in physics if you take physics. So if you can see how they cancel. The only problem with that is you have to kind of have a visual mind to see, well, how can I make them cancel? So that's maybe more of the challenge. Okay, let's try another one. Are we trying to dilute using a concentrate solution, a stock solution, or are we using solid crystals? Yeah, because it's asking how much solute we're using. That's probably referring to like how much grams we're looking for. It's actually really similar to what we just did. You guys see how we have a liters and a moles per liter sitting there? Put them together. 2.0 liters multiplied by 0.16 moles per liter. Hey, look, I just got rid of liters. That's like half the battle, just by multiplying them. But don't stop there. We don't want moles, right? Probably want grams, because grams is something we can actually tangibly measure in a lab using a scale. So let's find a molar mass. KCl. Potassium?
39.
3910, is it?
Yeah.
And chlorine? 3545? Hopefully you guys can see why I wanted to do a review unit, by the way. There's so many little skills that you need to have down pat before you can actually solve this question. Because you have to know what KCl is. You have to know how its molar mass works. Once you add it up, I got 7455. Then you have to know, well, how can I use that over here? Well, look, if I just write it as grams over moles, look, the moles will cancel. And the 7455 goes with the grams number. Hopefully you can visualize. This liter cancels that liter. This moles cancels that moles. The only unit left that hasn't canceled is grams. Something I can, in my lab, in an actual chemistry setting, I can measure. Like I said, I'm a big believer that we actually have to do the hands-on stuff. So that's why I want to make sure we do a lab later this week. So you can kind of practice the actual measuring part as well. Anyone get an answer? Okay, so we're going to need to round that, right? Because that's too many sig digs. This number right here and this one right here were not measured with nearly as much precision. We only get 2 sig digs of precision. So what did you say it was? 28?
23.8.
So 23.8 is going to round to 24 grams. So therefore, we don't need a very precise scale to measure this, actually. I can measure this on a very run-of-the-mill scale. Does that make sense? The scale for the last one right here that required 0.400 grams, that's an $800 scale. It needs to be very precise to measure all of those digits. This scale right here, 24 grams, that's a pretty cheapo scale. I can buy one of those at Walmart, 10 bucks. Okay, last one, then we'll be done for the day. What if I give you grams, and what if I give you a concentration and I ask you how much liquid you should add? How much of the water you should add? Now how do we solve a puzzle like this? Again, focus on your units. here I have moles per liter, and here I have grams. Right off the bat, do these things right here, will either of them be able to cancel something? Unfortunately not. Okay, so the link, though, is that we do have a way to convert a gram into something else. We can convert grams into moles. So why don't I start with that? 18.9 grams. And I could do moles over grams. Again, where do I find such a number, though?
Well, math.
I'm going to say that a lot. So sodium, 2299. You want 2 of them. Carbon, 1201. Just one of those. Oxygen, 16. 3 of those. Find a molar mass, which hopefully you can do fairly quickly. Like, I mean, look it up if you have to, but hopefully you know how by now. I got a molar mass of 105.99. Anybody else get 105.99? That's a G. Where does that number go? It goes in the bottom. It goes with the grams number because I want this grams to cancel with this grams. So this 105.99 goes here. I need to divide. What am I left with for units? Moles. Now, I don't want moles, though. What's the question asking for us to find? How much solvent? Solvent would be measured in liters. So I don't want moles, I want liters. So before I even type those two numbers in the calculator, I gotta keep going. If I don't want moles, I should put moles on the bottom. That'll cancel out moles, right? This one will cancel with that one. What am I looking for? Well, liters. So let's put liters on the top. Here's the issue then. Is there such a number that converts liters and moles? This guy right here. Where's the 0.67 go? Is it 0.67 moles in 1 liter? Or is it 1 liter in 0.67 moles? What does this mean right here? It means that you have 0.67 moles in 1 liter. That's what this number here refers to, right down here. So I know I have it written upside down, so it just means that in 1 liter, you need 0.67 moles. See how I flipped it upside down? I know that seems like in math, I would tell you, can't just flip a number upside down. But because I put units on it in chemistry, this is a valid way of solving it because it's just flipping the ratio. This 1 liter equaling 0.67 moles can either be written like this or like this. So this particular way is more useful. So now everything's canceled. The moles is canceled. The grams is canceled. So take 18.9. If you wanted to, you could times by 1. That's kind of redundant though. Divide by 105.99. You could times by 1 again, and then divide by 0.67. I'm running out of room. I got this 0.2661473, etc. Anybody else get that? Awesome. Okay, 2 last things then. I need to round this and I need proper units. 2 sig digs makes this 0.27 for my precision. And units, the unit that was left that didn't cancel was liters. So that is how much water you should add to make the solution. Usually when I give you questions, then I'm going to ask you for one of 3 things. If I give you a mass and I give you a volume, I could ask what's the concentration. That's one possibility. Second possibility, I could give you a concentration that you're aiming for and ask you for a mass, and then you find the volume needed to make that. Or I could give you a concentration and I could give you a volume, and then you figure out the mass. So usually it involves those 3 variables, a concentration, a mass, and a volume, because those are the things we can actually measure in a lab. Depending on the context, depends on exactly how you orientate these things. Sometimes you multiply, sometimes you divide. I don't like to give rules or formulas because I think it's way better if you can see how the units cancel. I think it's a more useful skill. And I know it extrapolates forward into other courses and other units. Any questions? Okay, quick summary then. Today we talked a lot about accuracy and precision. Those words to me are very important. Accuracy is, are you correct? If the answer is supposed to be 17 and you tell me that it's 37, you're not right. Does that make sense? But if the answer is supposed to be 17 and you say that it was 17.002, you're still correct, but you added more precision to it. Does that make sense? And so use those terms correctly because I'm going to test you on that a lot. Okay. The reason why that's so important is when we actually make stuff in a lab, we need to round sometimes and we need to use measuring tools. We have to use them properly, use them accurately, and we need them to be precise enough that the measurements they give are useful to use. And the second half of my lesson here was then being able to use some math. This is a very mathy portion for chemistry. And being able to convert grams and liters and grams per mole and moles per liter and work with all of those units interchangeably. So, tomorrow we're going to talk about how solutions can actually reach a saturation point where they're so full that stuff no longer dissolves. And then after that lesson, we're going to do a lab on Wednesday. And then Thursday's a work day. You guys know that you don't have school on Friday?
Yeah.
Good. And then Monday, we're going to do a quiz next week Monday. So that's what it looks like going forward. Lesson tomorrow, lab Wednesday, work day Thursday, quiz Monday. So, last thought here, and then you guys can start packing up or doing what you want. Here are some textbook questions if you'd like. However, I'd probably recommend the best thing you can do, take a look at your assignments and do a little bit of the assignment every day. You know how there's always like maybe 15, 20 minutes left at the end of a class? If you did like say one assignment question every day or two assignment questions every day, you'd be done. As opposed to like having to do the whole thing all in one sitting. So I think you should be able to do at least from 1 to 5, maybe even the next question or so. Other than that, there's 20 minutes left, so do what you guys need, I guess.